In this next module, I'm going to talk about looking at data, that is, graphing your data. It's always important when you get a new data set to graph each of your variables individually. When you do that, there's a lot of things that you can pick up from the graph. So you want to always plot your data, and what you're looking for are things like if you do a frequency plot of your variables, that what we're going to talk about in this module, you can immediately pick up things like, are there outliers? And outliers are just extreme values, very high or very low values that maybe are outside of the range that's expected for your particular population. Outliers, by the way, are not necessarily data errors, and we're not going to just throw them out. I always get students coming to me and saying, oh, can I call this an outlier and can I throw it out of my data set? We're certainly not going to throw outliers out, but it's important that we know that they're in there when we're doing a data analysis because they can be very influential on some of the statistics, as we'll see later this week. The other things that you can pick up off of a graphic are data points that just don't make sense. These are usually data entry errors. So if the data were entered manually, it's very easy for a data entry error to be introduced. Most data sets that are entered manually will have some of these. You want to pick those up as early as you can in the data analysis process. Finally, you want to plot your variables so that you can see how the data are distributed. What's the shape of the distribution? Where's the center? What's the variation? So you can get a good feel for your variables. Just to illustrate the importance of graphing and how easy it is to pick up some of these things from the graphic, I had a variable in my data set of my Stanford students where I asked them to report how many servings of fruits and vegetables they eat every day. So I went into the data set and made one data entry error. I took one of the values where somebody had reported that they eat 10 servings and I added a 0 just for illustration here. And you can see that it would be very easy when somebody's entering data for something like this to happen, a 0 to be added or left out. You can see how easy it is to pick up this mistake on the graph, right? It's immediately obvious that that point doesn't make sense. You can't have people eating 100 fruits and vegetables a day. So you would pick that error up immediately and be able to resolve it right away. The other thing you're looking for when you're graphing the data is just to describe how the data are distributed. So for categorical data, you want to pick up information like what are the ends, the numbers and percents in each of the different categories. And for quantitative data, you're going to be asking questions like, what's the shape of the distribution? Do I have a bell curve or skewed distribution? Those are some of the things we're going to be talking about in this module. Where's the center of the data? What's the spread or variability of the data? The frequency plots that I'm going to be showing you, these are for plotting one variable at a time. For categorical variables, I'm going to show you a bar chart. Most of you are probably familiar with a bar chart. They're fairly easy to interpret and make. For continuous or quantitative variables, I'm going to show you about two types of plots. There's something called a box plot and something called a histogram. And I love histograms. You're going to be seeing tons and tons of histograms in this course. So it's important that you pay attention in this module so you really understand what's going on in a histogram. You'll probably be dreaming in histograms by the end of this course. So first of all, a bar chart is used for categorical variables. Again, it shows the frequency, that is the count or proportion of observations in each of the categories. For example, I asked the students in my Stanford data set, did they play varsity sports in high school? 30 said yes, 20 said no, and that's very simple information to pick up off the bar chart. Also, I created a categorical variable for coffee drinking. I divided people into none, light, moderate, and heavy coffee drinking. And you can see the frequency counts shown in a bar chart here. The way that I divided the categories, I ended up with fairly even numbers in all of those categories. Again, very easy to look at and interpret a bar chart. For quantitative variables, we're often going to use a box plot or a histogram. And again, this is to show the shape, center, and range of variation of that quantitative variable. So we're going to start with a box plot here. So here's the box plot for exercise. I asked the students to report how many hours of moderate to intense exercise that they do every week. And you can see that my Stanford students were doing pretty well on exercise. Most of them are getting a decent amount of exercise weekly. The way that you interpret this box plot, so first of all, the box is the middle 50% of the data. So if you were to arrange the students from the lowest exercise per week to the highest, that would represent, the box would be those who were right in the middle 50%. That is from the 25th percentile to the 75th percentile. So the 25th percentile here is 2, the 75th percentile is 6. So that means that 25% of my students were doing less than 2 hours of exercise per week, 25%, a quarter of my students were doing more than 6 hours per week. The middle 50% was between 2 and 6. The line in the box represents the median. That's the 50th percentile. It means that 50% of my students were exercising more than 3¼ hours a week. 50% of my students were exercising less than 3¼ hours a week. The distance from the bottom of the box to the top of the box, from the 25th percentile to the 75th percentile, that's called the interquartile range, or sometimes we abbreviate that as IQR. So I'm just going to subtract 6 minus 2 in this case, and we see that the interquartile range is 4. The middle 50% of my data, the spread of that is 4. So that part's actually fairly straightforward. The box is fairly straightforward. It gets a little more tricky when we talk about the whiskers, so I'm going to start with the top whisker. The top whisker can be one of two things. It's either the maximum value, or it's this other quantity, which is the 75th percentile, or Q3, plus 1.5 times the interquartile range. I'll calculate out what that is in just a second here. But you're going to pick out of those two. For the top whisker, you're going to pick whichever of those is lower. If the maximum is lower, you put the whisker at the maximum. If the Q3 plus 1.5 times the interquartile range is lower, you're going to put the whisker there. So let me just calculate what that is here. So again, the interquartile range is 4. So 1.5 times the interquartile range of 4 gives you a value of 6. And what we're doing here with this value of 6 is we're saying that if you are more than 6 below the 25th percentile or more than 6 above the 75th percentile, you're kind of outside the expected range for this population, and we're going to call you an outlier. There actually are no outliers in exercise. We're going to see in another variable, we're going to see some outliers. So in this case, the third quartile, the 75th percentile, occurred at 6 hours. The 1.5 times the interquartile range is also 6. So this boundary, this value here is 12. It turns out, though, that actually the maximum value was also 12 here. So those are equal in this case. There was a student who exercised 12 hours per week. Since both of those are equal to 12, obviously we're going to put this upper whisker at 12. For the lower whisker, the lower whisker will occur at whatever is higher out of the minimum value, or the 25th percentile minus 1.5 times the interquartile range. You're going to pick the higher of those two and put the lower whisker there. So in this case, the 25th percentile occurs at 2, minus 6 is equal to -4. So this boundary would occur at -4, but of course we can't have -4 hours of exercise per week, so this whisker will occur at the minimum, which is 0. There were some students who didn't do any exercise per week, so we put the whisker at the minimum. So in this case, with this box plot of exercise, the whiskers just represent the minimum and maximum values. We're going to see in the next slide that sometimes the whiskers will represent this other quantity. So I also asked my students to report for me how they rated themselves on their political leanings. And I had a scale that was anywhere from 0, where 0 is the most conservative, up to 100, where 100 is the most liberal. And I asked my students to rate themselves on that scale. You can see by looking at the box plot that the majority of Stanford students cluster in the liberal range, in the Democratic range. And if we just zero in on the box here, the 75th percentile occurred at 85, the 25th percentile occurred at 68. So that means the middle 50% of my students ranged between a value of 68 to 85. So that's very much in the liberal Democratic range. The median occurred at 78, so half of my students rated themselves higher than a 78, half rated themselves lower than a 78. The interquartile range is just the distance from the 25th to the 75th percentile, so that's 85 minus 68, or a value of 17. So actually that's a fairly narrow range here. My students are really clustered up in that liberal range of values. Now, in terms of the whiskers here, the upper whisker occurs at the maximum possible value of 100. So one of my students said that they were 100, as liberal as it comes, and so I'm going to put the whisker there. If I were to calculate the third quartile plus 1.5 times the interquartile range, that's 85 plus 1.5 times 17, obviously that's going to be higher than 100, so the maximum is the lower of those two values. We're going to put the whisker there. There's nobody who falls outside of that 1.5 times the interquartile range boundary. For the lower whisker, however, notice it's different because the lower whisker here is not at the minimum value. So if you calculate the 25th percentile minus this 1.5 times the interquartile range, you get 68 minus 1.5 times 17. That's a value of 42.5. So we're going to put the whisker at 42.5 because that's higher than the minimum value. The minimum value actually occurred at 27. So what this is saying is that given the rest of the people in this sample, anything below 42.5 is kind of unexpected for this data set. These people, if you're outside the expected range if you're lower than 42.5. We're going to call those people who fall in that range lower than 42.5, we're going to call them outliers. And we're going to represent each person who is an outlier with a dot. Now, what do these outliers actually mean? There's 4 people here. Again, the lowest occurred at 27. So what do those outliers mean? That doesn't mean that those are not data errors. There's not problems with the data. Those are real people, and that's probably really their political bent. So these, again, are not errors. It's just that most of Stanford students are more in the liberal range. So anybody who's at 27, 30, and even low 40s is outside of what's expected for Stanford students. Again, we're not going to throw them out. Those are real data. Those are real. There are really Stanford students who are Republicans. And clearly they may be outliers for this particular population, but if you went elsewhere in the country, say you went to the Midwest of the US, in fact, it might turn out that that range is quite common out there. And so people who have values of 27, 30, 40 may not at all be outliers in a different population. But again, it's important we know that those outliers are there because they can have a lot of influence, a lot of sway on certain statistics, as we're going to see this week. So that's the box plot. Now I'm going to show you the histogram. So I took that same variable exercise and I put it into a histogram. So a histogram, the way you build a histogram is you take the range of values. So in this case, exercise ranged from 0 to 12, and you divide it up into equal intervals. So in this case, I made, and we call those bins, I made bins of 2 hours per week. So I divided up exercise into 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12, 12 to 14. And then what this graph shows you is what percent of my observations fall within each of those bins. So the y-axis here is a percentage. It's the percent of observations that occur within each of those bins. And you can see by looking at this graph, it's immediately obvious that most of my students, the biggest number of students, fall between 2 and 4 hours of exercise per week. So it's just a really nice graphic because you can immediately see kind of where everybody lies. Let me go into a little bit more detail about how to read this graph. So again, the y-axis is a percentage. So you would scroll across, for example, for this lowest bin, the 0 to 2 bin. If I scroll across to the y-axis, I see that intersects the y-axis at 12%. The height of that bin, the height of that bar is 12%. So that means 12% of my students, and remember I had 50 students, so 12% is equal to a count of 6. So 12% or 6 of my students exercised between 0 and 2 hours per week. And in fact, it's actually between 0 and just up to 2, but not including 2. It happens to be that this statistical program, the higher value in the bin is not included in that bin. So it's going to be 0 all the way up to, but not including 2. 2 is going to be, anybody who's exactly 2 will be included in the next bin. So you just have to know that about the way that this particular program groups things. So you'd read the next bin, which is obviously the highest, that bar has the highest height, as 42%, so that's 21 students. 42% of my students exercise somewhere between 2 and just up to, but not including 4 hours per week. And you can read across all the bars in the same way. I'll just read the very last one here for you. So it turns out that there was one student, 2%, who exercised exactly 12 hours per week. That person got included in the 12 to 14 bin because, again, the 10 to 12 bin does not include 12. So 12 to 14 is the bin that actually includes exactly 12 hours per week. So that represents one student who exercised 12 hours per week. Now again, there's just so much information that you can pick up visually here. So notice that this distribution, the shape, has what we call a right tail or a right skew. All this means is that most people exercise a couple of hours per week, but there's a few people who are really heavy exercisers and they form a tail out to the right, a couple of high values out to the right. So we call this a right skew or a right tail. I just want to show you what happens if I change the bin sizes. So what if I were to set the bin size to be really small, like 0.2 hours per week? You can see that this graph is not as visually appealing. It's harder to pick up the pattern from looking at this graph. So this graph really just has too much detail. If you make the bins too small, you end up with too much detail. It's not as helpful. Similarly, if you make the bins too big, let's say I set them to be 8 hours per week each, again, in this case, there's too little detail, and you're not able to pick up all the important details from this graphic. So it's a little bit of an art selecting the right bin size. It turns out that most standard statistical programs have an algorithm that will choose the bin size for you if you don't want to choose it yourself. Or you can control that bin size yourself to get just the right amount of detail in there. So those are the histograms for exercise. Let me now show you the histogram for political bent. So again, as we saw with the box plot, you had a lot of students clustering in the liberal democratic range. That is in between 50 and 100. And you can see that the shape of this distribution, we could say it has a little bit of a left skew or a left tail. That is, most people are in the 70, 80, 90 range, but we have a few lower values out to the left. So you might describe that as having a left skew. You could also describe this distribution as being bimodal. That means it has two peaks or two groups. And that's actually pretty informative to see it that way. Because what's going on here is that I really do have two types of students, two groups of students in terms of politics. I have a large group of Democrats at Stanford. And you can see that within that group of Democrats, if you just look at the distribution of political ratings within my Democrats, those ratings actually follow a pretty nice bell curve. So what that says is Democrats at Stanford hover around a liberal rating of sort of 80, that's kind of the mean, but we have some who are more in the 60 or 70, that's the left tail, some who are over in the 90, 100, that's a right tail. So it actually follows a pretty nice bell curve. So that represents my Democrats at Stanford, but then we also have a second group. It's much smaller, but it does exist. We have a second group of Stanford students who are Republicans. We have a population of students who are Republicans. Interestingly, the political rating within the Republicans also follows a normal curve, and it's centered around 40. So you can see that the Republican group at Stanford is not highly conservative, right? 40 is actually quite close to 50. So they're a little bit in the conservative Republican range, but they're hovering around 40, which is rather high in that range. And then we've got some who are out in the 30s and down to the high 20s, and some who are up to, high 40s and low 50s. So again, though, it's interesting to see that there's really two groups here.